In this video, we're going to run 100,000 simulated seasons of the Premier League to estimate each team's chances of lifting the trophy. Simulations let us quantify uncertainty, things like injuries, form swings, and match to match randomness that no single prediction can perfectly account for. This approach is the backbone of most modern forecasting systems, where instead of predicting one outcome, we simulate thousands of possible seasons and look at how often each team finishes on top. The key to these simulations is having a reasonable estimate of how each remaining match is likely to go. For the home team, for example, there are always three possible outcomes. They can win, draw, or lose, where each event has its own probability, which we will for short write with the letter P. So P parentheses home win is shorthand for the probability of a home win. To get these outcome probabilities, we need to think in terms of possible score lines. For simplicity, let's assume each team can score at most 3 goals. In this grid, every green square represents a home win because those are the score lines where the home team had more goals than the away team. But each of these score lines has its own probability, since a 3-0 is much less likely than a 1-0. So let's zoom in on the 3-0 case to drill down into this a little bit more. The probability of a 3-0 scoreline is the probability that the home team scores 3 times the probability that the away team scores 0. This multiplication only works if we assume that the number of goals scored by the home and away teams are independent, meaning one team's scoring doesn't directly influence the others. And though it's not a perfect assumption, it does work very well in modeling football statistics. The question now becomes, how do we actually figure out the probability that a team scores a certain number of goals? To answer that, we need to talk about something called the Poisson Distribution. Imagine you track the team's goal output for, let's say, 250 matches, and you made a bar chart showing how often they scored 0 goals, 1 goal, 2 goals, and so on. This bar chart, called a histogram, would start to form a very recognizable pattern. Scores like 0, 1, 2, or 3 goals happen quite often, whereas more extreme scores like 4, 5, or more goals happen much less frequently. And if you keep collecting the data, the shape begins to stabilize. That's exactly what you're seeing happen in this animation. We're sampling goal counts over and over, and the bars naturally settle into the classic shape of the Poisson distribution. That yellow symbol at the top in the box is the Greek letter Lambda, and it represents the average number of goals we expect per match. And for the Poisson distribution, this average also ends up being right around the goal count you see most often in the long run, which is exactly why the bar centered around 2 goals grows the tallest here. Now, to turn these raw counts into implied probabilities, we simply divide each bar by the total number of matches, 250 in this case. And when we do that, we can see that scoring 2 goals has the highest estimated probability of around 30%, followed by the second highest being about 1 goal at 25%. Even though our bar chart, aka the histogram, gives a good approximation of the goal probabilities, the true distribution is what you get if you could take an infinite number of games. When that happens, the bars settle perfectly into the smooth yellow Poisson curve you see here, and this curve gives us the probability of scoring any number of goals k for a given average rate lambda. Remember that Greek letter from earlier. And that's exactly the formula at the very top. It gives us that probability that we're looking for. Now, suppose lambda is 2 and we want the probability of scoring exactly 2 goals. So in this case, both k and lambda are 2. We're going to work through an example to build our intuition. We're going to replace k with 2 in this formula now and work it out. The final result is 0.27, which means that there is about a 27% probability of scoring 2 goals. And notice that was very similar to the approximate 30% we got with our histogram. As a note, in these formulas, that letter E is actually not a letter, it's Euler's number. And it's similar to pi, where we use a symbol to represent it because it has an infinite amount of decimal places, but it's about 2.72. And that exclamation point is called a factorial, and it's just the product of all the counting numbers leading up to the number in the factorial. So for example, 3 factorial is 1 times 2 times 3. Now, if we look at how the curve shifts for different values of lambda, we see a very clear pattern. Smaller values of lambda peak at a lower goal count, while larger values of lambda shift the entire curve to the right and peak at higher goal counts. And let's dive into this a little bit more with a side by side comparison. Let's compare two Poisson curves side by side, one with lambda equals 2 and one with lambda equals 3. You can think of these as representing two different teams because not every team scores at the same rate. A team with a higher attacking output will naturally have a higher lambda. To make this more concrete, let's look at the probability that each team scores exactly 3 goals. For lambda equals 2, the chance of scoring 3 goals is about 0.18 or 18%, while for lambda equals 3, that probability is around 22%. This example makes it clear that lambda is really capturing the expected goals per game of a team. So teams with a higher lambda are more likely to score more goals. And this difference becomes even more pronounced as we look at bigger score lines like 4 or 5 goals. So what actually determines the value of lambda, the expected goals per game for each team? Note that this value will shift from game to game, and it is a combination of a team's attacking strength, the opponent's defensive strength, and whether or not the team gets a home advantage. A team's attacking and defensive strengths are computed by benchmarking each team's expected goals for and against per match against the league average. For example, if Arsenal are playing Wolves, their strong attack combined with Wolves' weaker defense will push Arsenal's expected goals or lambda higher for that match. But if Arsenal are playing Manchester City, the opposite happens. City's strong defense will pull Arsenal's expected goals lower, giving them a smaller lambda for that game. Now, the factors affecting lambda were not a complete list, but they were enough to demonstrate the main idea. Now we can put everything together before showing the predicted league winner. Let's look at an example match where the home team has a lambda of 1.8 and the away team has a lambda of 1.2. Using our framework, we can compute the probability of every possible scoreline shown. Here we'll assume each team can score up to 4 goals, just to keep the illustration manageable. Each square in the grid shows the probability of that exact scoreline. Because only one scoreline can happen in a match, these events are mutually exclusive, which means that the probability of a home win is just the sum of all the probabilities of scorelines where the home team has more goals than the away team. In our case, that means just adding all the probabilities in the green squares. And when we do that, we get a value of 0.48 or a 48% chance of a home win. Just as a reminder of how we got each of the probabilities in each square, let's look at the very top left one, the scoreline of 4-0. This would be the probability that the home team scores 4 times the probability that the away team scores 0, which using our Poisson formula would be the product of the two terms that we see here. Now, if we instead sum the yellow square probabilities, we will get the probability of a draw. And if we sum the red squares, we get the probability of a home loss. Together, these three numbers add up to 100% of all possible outcomes. These percentages are the foundation of our entire simulation. They tell us how likely each match is to produce 3 points for the home team, 1 point for both teams, or 3 points for the away team. Now that we can estimate the probabilities of earning 3, 1, or 0 points in each remaining Premier League match, we can run 100,000 simulations to estimate every team's chances of winning the title. This approach, running many randomized simulations to approximate real world outcomes, falls under a class of statistical techniques called Monte Carlo methods, which were first developed during the Manhattan Project for nuclear research. From these results, we see that Arsenal emerges as the clear favorite, though several other teams still retain small but non-zero chances of lifting the trophy. To be specific, I will now show the top 5 teams with the highest chances of winning. Please note that these results are for educational and entertainment purposes only. They should not be used for betting. Of course, these probabilities aren't perfect. Our estimated match probabilities can always be refined with more sophisticated models, more detailed data, or better calibration. But for demonstrating how Monte Carlo methods are used in sports analytics, this framework is more than enough. These technical improvements can always be layered in later. One final note, these simulations take the league table as of match day 15 and project forward from that point. Unexpected events like injuries, transfers, tactical changes, and change in form can shift title odds dramatically. But at least for now, it seems like a very good year to be an Arsenal fan.
Oh, yeah. Hey.
Thank you guys for watching. Please let me know in the comments if you have any questions or suggestions for another topic. Please don't forget to like, comment, and subscribe. Thank you.
Hitting new levels will come on the bezel, the 9 on the iron, the rock heavy metal, whoa. Hey, yeah, hey. Hitting new levels will come on the bezel, the 9 on the iron, the rock heavy metal, the fire and the power, I grind by the hour, we working on building the whole them in power, the signs in the stars, mine is on Mars, nigga like Tesla, life.